Oops. The lower bound is actually redundant, so that's an exercise. So I checked the argument for this theorem, and it didn't require lower deregularity. It didn't require this inequality, but then maybe I missed something. So that's something for you to think about. We have some open-ended exercises. Okay, so this is somehow not surprising, right? So if you have a nice kernel, you should be able to smooth out the drops in the potential created by this kernel. And of course, if you have something that's continuous, this is not an issue altogether. So if you're close to continuous, then a statement like this should hold. Okay, so one interesting side effect to this. Okay, so are there any questions or doubts about this exercise? So the exercise is specifically to fill in the proof of this statement. Okay. So this condition, Grossman's condition, is a first order condition. Okay, what does it mean? So you're effectively taking the first variational derivative of your functional right, and remember the functional was this. So the natural question is, okay, what is the second order condition then? Right, so everybody took calc whatever 2, 3, or the similar course that's taken in Europe. And so the idea is, okay, can we compute second order derivative that would give sufficient conditions for the minimum, or at least something that's similar? So here's a question. So we do not expect that it will have anything to do with this integral, obviously, because the integral, as you certainly realize, is just linear in mu, right? So when we think about second order conditions, we just drop the second term. Okay, so I can get rid happily of that noise, of that annoying v at this point, and just focus on the double integral. Okay, and let's see. So here is an exercise, or yeah, this is going to be an exercise, I think, although I'm going to discuss it a little bit. So partial answer to this question. So if you ever have to minimize a continuous energy, right, an integral energy like this, then like Ed explained, right, at length. So Ed showed these examples where, okay, you do a lot of work and then you find a measure that makes potential constant on your working set, right? And then you're done, assuming that you have some convexity for the kernel. Right? So basically that convexity for the kernel that Ed used implicitly, and I think Sylvie also invoked at some point. She said, okay, look, this is a nice kernel because it's convex. So the convexity comes effectively from the following property. Okay, so if you have this mu0, and again, I'm going to say it's global. This is not quite necessary, but should be fine. If you have seen this, you know what's coming. So let's say this functional, which, okay, maybe I'll give it a name or something. So this is functional I. Then, so the question is, how do you write the second variation of this integral, right? And if you think about this a little bit, or if you have seen this, you realize that, okay, well, it's something like a quadratic functional in terms of mu, just like this guy was a linear functional in terms of mu. So it's unsurprising somewhat that the second variation of a double integral is also a double integral. So we're still talking about variation. So if you argue similarly to how we would argue to prove Frostman, so you want to perturb your minimizer mu0 by a signed measure, right? And to do that, while staying within probability measures on your set A, you're going to add signed measures which are also supported which are supported inside the support of mu0. So in other words, for any signed null of total mass 0, right? So nu of A is 0, and such that their support lives inside that of mu0, you have this natural inequality. So if you evaluate the same double integral, right, but for nu this time, then what can you say about this integral? Okay, any guesses? Okay, I don't want to ask for guesses because Mirta obviously knows, and everybody, well, I would guess most people know. So respond to this question only if you don't know the answer. Okay, so this is like a second derivative at the minimizer. So this should be the inequality, obviously, right? So this an exercise is to prove this. If you haven't seen the proof, if not, let's look at what kind of things you can do with this. So just as Frostman, right, you would expect that the second order condition is rather weak. Right? So it's a very general fact, holds strictly speaking for any kind of measure. Nice measure metric spaces. So very, very general statement. So it should be rather useless, right? It should be mostly not very helpful. So what kind of things can you actually do with it? Well, it turns out that at least for some kernels, you can establish some quite helpful things. So I'm going to regurgitate my slides here and bring up this. Okay, so this is going to be the actual exercise for this type of functional. So let's say the kernel K is not singular anymore, right? It's still you can think of it as repulsive, but it's very weakly repulsive. Right, so the profile of K, so let's say K is again radial, Okay. Radial, but it's the repulsion that occurs at 0 is very, very weak. Right. So you see, this is the condition. So basically, you have a 0 of order 2 plus, right? So at least 2 at the origin. So this is R. This is, let's say, f of R. So very, very weak repulsion. Right. So it turns out that just using this very, very weak-looking fact about the second-order derivative, second-order variation, this integral functional, you can establish a quite interesting fact, which is that if you take a compact set A and minimize something with a very, very weak repulsion in it, then charges, instead of being repelled, they will cluster. Right. So for some reason, if repulsion is too weak, it's okay to cluster. So I feel like there is some moral here that's more from social sciences or something than from math, but let's not dwell on it. So if the repulsion is very weak, it's okay to get together. And so other questions. So maybe if people don't want to read this, maybe we can just see if the idea makes sense to everyone. Because I'm going to shamelessly rip the explanations from my slides. So this is what you could have seen during my mini talk, but fortunately you didn't see. So now, oops, it comes again, comes back to bite you. So how will this work? So the idea is this: you basically pick a suitable discrete measure, right? A suitable discrete signed measure. You pick a suitable nu in this notation, right? And you basically just write the integral of this form, right? And then verify that if if there is no clustering, right? So then there is a if your measure is not supported in a finite number of points, then there's a concentration point in the support, right? And so you basically use this fact to pick 3 sufficiently close points to serve as the support of this nu. Right? And then use this very weak repulsion to find to violate the inequality here. Right? So instead of greater than or equal 0, you end up with something that's not going to work. Right? So you argue, let's say by contradiction, you say, let's say everything is good. I'm going to write this measure, and then I can change weights however I like, which means that the quadratic form like this is positive definite, and then I will arrive at a contradiction. So without maybe going into too much detail, but just a little bit detail. So so you write the matrix with the values of your kernel. Okay, so for some reason I used capital F instead of the small f. So this is the small f to us. So you write the matrix, basically the covariance matrix. The k evaluated at every pair of points xi, xj from the support of nu. That has to be positive definite. You write the positive definiteness condition. Replace f. So f is in the first approximation, something like this, with alpha bigger than 2. And that will be the point of failure. How exactly? Well, basically because the direction of convexity for alpha bigger than 2 is going the wrong way, and you will fail, right? So you end up with something like this. So here we're going to write, okay, so here, let's say you have 3 points in the support, right? Like I said, because your measure is not finitely supported, it has a concentration point, right? So it has a sequence of points converging to a limiting point. Let's say call that point X, and then you have 2 more points Y and Z, however order you like. Having written this covariance matrix on these 3 points, you have a condition like this, right? You optimize over all weights, over all admissible weights. So of course there are some conditions because you can only use signed measures of total mass 0 and so on and so forth. But the moral is you end up with something that looks like so, where you will have 2 distances which are let's say 2 distances, let's say Y and Z. So let's say everything is going, you have a sequence that clusters close to X, right? And then you end up with the with some sort of acute angle in your clustering sequence, right? Which means that you have a triangle which has very acute angle somehow, right? And then that results in a wrong inequality like that. So okay, so obviously I don't want to bore you with the details. Long story short, there's a violation of positive definiteness occurring in the support, assuming that the repulsion is sufficiently weak. So what are the conclusions, right? So what did we achieve with our very weak second variation property? So the interesting conclusion, I thought, was that this holds on arbitrary metric spaces. Well, okay, so you have to be a bit careful here. So on arbitrary Alexandrov metric spaces, right? So basically, you have a metric space with curvature bounded below. So if you think about any imaginable manifold, such a statement applies, right? And there we are. We have proved something, extremely general for optimization problems on extremely general sets, possibly with very, very relaxed smoothness conditions and so on. Now, the question is, can you make this? Can you improve on this in any fashion? Right? So this is a fairly recent result. Can you improve on it in any way? Well, in some sense, the improvement predates this result by about 70 years. So there is a result due to Goran Bjork from the 50s, which says that if you maximize an interaction that looks like so, let's see. So this is going to be maximized because my lambda here is bigger than 2. So you may be thinking right now, okay, why do I care about this sort of literature overview? Well, there is an interesting phenomenon occurring here in this literature overview, right? So this is the the functional that is being maximized. And let's say a compact set A, right? So mu lives inside the set A. Then well, okay, this is compact, so probably strictly included in our D. So the global maximizer lives on at most D+1 points. And okay, you're free to treat this question as an exercise as well. So this is rather tricky. So the measure that maximizes something like this lives on at most D+1 points. And so the reason I said there's an interesting phenomenon. So remember with the literature here. So remember we talked about Gegenbauers and so on, and I said there was a result due to Schoenberg from 40s. Bjork uses some results also due to Schoenberg from 30s, right? Which concerns some seemingly completely unrelated stuff, where Schoenberg basically studies which changes of metric in a metric space allowed to embed it. So basically, which metric spaces can be embedded inside a Hilbert space? Which changes of metric in Euclidean space allowed to embed it, still allowed to embed it in a Hilbert space. So this also has something to do with preservation of positive definiteness and so on. So this is quite, I thought, quite amusing. Okay. Another slightly easier exercise that I'll state here. Well, okay, this is actually not slightly, but this is quite a bit easier. So use, let's say, right, so we have the second variation property, let's call it something. 2 stars, right? So use 2 stars for local minimizers. Okay, you will ask what kind of local minimizers. We talked about global minimizers before and so on. Well, so you should pick your favorite metrization of weak star topology on compact sets and use that as the metric. So here implicitly you have to show that 2 stars also holds for local minimizers, right? So this is requires some minimal effort to verify. But anyway, so once you establish 2 stars for local minimizers, which if you know how to establish it for global minimizers, you also know how to do it for local ones, to show that 2 local minimizers let's say measures mu1 and mu2 with distinct values of our functional on them cannot be nested. Okay, so where I'm going with all this, right? So we have seen before how to use first order condition, which is Frostman, to find minimizers, right? In situations where there was uniqueness. So as soon as you find something that is constant on the entire working set, you're done. And that I said was due to convexity. So there are several questions which I didn't touch upon. There are these convexity issues or questions of convexity, which there are at least two convenient notions. So one, convexity is due to positive definiteness of the kernel, right? And this is the one that Sylvie referred to. And then there is another one, which is a convexity with respect to displacement. Right, so this, so basically, you should think about interpolation in terms of optimal transport, and that interpolation also gives you a notion of being convex. So if you have any notion of convexity and you can show this Frostman style equilibrium condition, then you're done, right? But of course, there is the shortcoming of many of these methods, that they don't really take the geometry into account that much, or at least I'm not aware how to use it in a convenient fashion. Okay, sorry, I'm fighting with the window here. Convexity principle, blah blah blah. Okay, so so these are some applications of classical potential theory. I have also faithfully pointed out how they can fail, right? So if you need to study some fine geometry of the minimizer, you're probably better off thinking about PD of the optimization problem rather than this abstract sort of either of these abstract variational principles. And so I think this is a good place to stop. So if I accidentally didn't use all of my time, which I think I did, but I'm not totally sure because I don't remember when I was supposed to stop. Even if I didn't use all of my time, I'm sure nobody will be angry at me for that. So thank you very much.
Thank you very much. You use all about 20 seconds, so it's pretty good. At least according to my clock. And are there any questions? Yeah, there is a question. We talk more about the displacement convexity. We talk more about displacement convexity, what it is used, etc.
Yeah. So okay. So this is so there are two options, right? The positive definiteness, it comes from something like this. Let's say. So I know I started with the wrong one, but I'll show you how they are different. Right, and then maybe dx dy. So this is so one notion comes from positive definiteness of the kernel, right? The other one is basically okay. So this is convex in the first sense. A functional that would be convex in the second sense is something like this, right? And here I'm thinking of measure rho dx. So this is my density being sent to this value here. And the second sends rho dx to, let's say, rho 1 plus 0.01 dx. Right? So if you're asking specifically what kind of interpolation we're using, well, you take one measure, mu1, and then you take another measure, mu2, right? And then there is some matching between them, which can be given, for instance, by optimal transport, right? And okay, so the matching means you draw lines that go from every point of the support of this measure to the corresponding point of the support of this measure, and the different lines do not intersect, because otherwise you could transport one into the other in a better fashion. And so the way you interpolate is like this. So at time 0, you start at this measure. At time 1, you end up at this measure. At time t between 0 and 1, each point from this measure travels a fraction t of the distance to the corresponding point in mu2. Right, so that's the displacement interpolation. Right, and if you use this type of interpolation, then something like this will be convex. So the common feature of both of these convexities is that I think they both show up in Lieb's papers, something like 30 years before they show up in math papers. Or at least that's kind of my understanding.
The second one, the cleaner, is that function you described is convex in T for every mu1, mu2, right?
Yeah, yes, yeah. Mm-hmm.
The first one is convex in rho, the second one is convex in T.
Say that again.
The first one means convexity in a row, convexity in the measure. The second one is convexity in T for any two measures.
Okay, right. So the point is, you have a way to interpolate between pairs of say pairs of probability measures. Right. So okay. So this gives you a path on the space of probability measures that connects mu1 to mu2. Right. The corresponding path for this guy would be this, right? So I just showed you how to interpolate in the sense of displacement. Let me show you how to interpolate in this sense, right? In the sense that corresponds to this first convexity. So you would just take, so the interpolation would do this. So you take mu t, and again, t is between 0 and 1. So it's again some sort of interpolation, and you just take a linear combination. So let's say 1 minus t right. So now you see, okay, both give you some sort of curves in probability measures, but the curves are quite different. Right, so obviously you can see that, for instance, some sort of intermediate measure here would look something like this, whereas intermediate measure here, well, it looks exactly like mu1 and mu2, but reweighted, basically. Yeah, I don't know if this resolved your doubts. So
Yeah, pretty much.
Okay. Are there any more questions? I think let's thank Alex. Thank you, Alex. It was very nice.
right, thank you.